Hello, hello from me, from my side also. That was an excellent presentation from Hussein Bahia. A lot of information, a lot of new information. For Estonians who are here present today, we spoke a little bit about that, our results from when we were in the Asfaldiliidu päev or Asfaldipäev in the autumn time. So we had some results over there, and now we are going to present the updated results. What have we done so far from that time to here? We cannot present to you the final results for our study because it's not final yet. It's in April, we have a deadline. We have, though, some ideas or a vision where should this study stop. So we have some ideas, vision, what are the final conclusions, but we will not reveal those today. So my name is Sven Sillamäe. I'm going to speak about bitumen research in Estonia. We would like to especially thank for Estonian Road Administration for funding this study. I am not alone in this study. We have a very good company doing together this one, and we are working together in close relationships. Also, not only Estonians work with this study, we have many consultants. As you saw, one consultant just before, UW Mark Professor Hussein Bahia, and his co-worker Puya, cannot pronounce his last name, so that's difficult. Then we have a Queen's University from Canada, Professor Simon Hesp. We have had some contacts from Delft University, and also we have a good cooperation with Norwegian University of Science and Technology, NTNU, as I'm conducting some studies over there and having good consultants over there. Just, I wanted to small remark in this place. A lot of my students are present in here, so I have to apologize for them for not being for them in school. And that is the reason why I have not been in school, and you have had to make your studies by your own in e-learning course with my materials prepared for you, as I have been in NTNU with this project. But you know, teachers have to also educate themselves, and participating in science and research, that's an excellent way to do that. Well, about motivation, why we started the project. Ivo Adamson already said that there's a some suspicious that bitumen quality in Estonia is bad. If we can say bad, or the quality is not good enough for our climate, and somebody does something wrong, and we don't get the product we would like to have it. So we wanted to check that. Also, we've got some feedback from the field. Contractors have told that bitumen with penetration 7100, that is mostly used in Estonia, or only bitumen grade in Estonia for asphalt concrete. This penetration 7100 is not the same than some years ago. So they have developed some knowledge about this bitumen, and this knowledge doesn't work anymore today. So there's a suspicion that could there be something wrong. But tests according to European norms, they are always in the required limits and show no significant differences. But we know that in the reality there are very many significant differences. When you run the plant, you can feel and touch different bitumen. EN test results show the same results, but in the reality, in the plant or in the field, the results are not the same. For surface dressing, Marek and Rein are doing a lot of surface dressing in Estonia. They have told that bitumen is very brittle around 0 degrees, and especially first winter is problematic. A lot of stones are raveling, and bitumen doesn't hold the stones together. And work quality difference in the same conditions within 2 years in a row. That means that when you stop, you have exactly the same road. You stop in 1 year in this place and you start exactly with the same conditions, exactly with the same aggregate, exactly with the same bitumen. You start at the same point and the work quality is not the same anymore. Also, we can see some defects, cracks already after 2 to 4 years on our road payments, but according to EN test, everything is okay with bitumen again. So we have a question, is it about binder? It has to be, or doesn't it? Binder is the most expensive component in asphalt concrete, but on the other hand, it's a component with the least knowledge we have. So it's very easy to suspect binder. Is it about binder? We can feel the aggregate. We know more or less the aggregate properties, but how much do we know about the binder? So is it about binder, about those problems I raised up? Are tests according to European regulations or European norms done by Bitumen, are those tests and quality control and test results, are they enough, or do we need something else? Do we need completely different approach to have a bitumen properties to measure it? Do we have to turn a different page? Do we have to forget those EN tests and look something else? So that was the question we have. And then the most hard question, what is good binder? How to define good binder? What are the properties of good binder? What are the limits of those properties, and how do you do the measurements to get those properties and to get those limits? What is the good binder? We haven't got an answer, we didn't have an answer at that point. Now I forgot the word. Yeah. We would need to have more improvement of bitumen knowledge in Estonia. We have to be honest with us that overall knowledge has been poor, even in the sense of basic EN tests. We do the tests, but we cannot read the tests. We cannot relate those test results to the overall performance that bitumen have. We would like to have more information about bitumen. We would like to have more information about what we are dealing with. We can say that bitumen is not a black mysterious liquid. Bitumen is a very important product for long-lasting roads. So we would need to have more knowledge about it. We would need to have knowledge about what is good binder, how to measure the properties, how to measure the limits, and how to measure it in the correct way to have most information out of it. So these were the motivations what we have, or what we had to when we started the study. We have hypothesized that bitumen quality in Estonia is poor or have gotten worse over the years. We hypothesized that tests done in our labs according to European norms, but are applied to bitumen binders, does not represent bitumen real behavior, and we are unable to predict payment performance according to these. And we hypothesized that performance grade tests, PG, the test what Professor Bahia just spoke about, that these tests give the information what we need. So that was the starting point where we started to build up our study. What we have done, we took 8 binders what are present in Estonian market and what have been used or what is being used in here. We have 5 binders with penetration 70-100. We have 2 binders with penetration 160-220, and also we included 1 Estonian oil shale binder, which is a local product. To evaluate these properties, we made all the tests according to European normative with a neat binder test, and also we included tests what have been meant to use for modified binder. We have done all North American PG creating tests, as Hussein showed you, and also we did needed modification to meet those requirements. Then we did some extra testing proposed for PG modifications. These are linear amplitude sweep tests, LIS. Then there's a single edge notch beam, SENB test. And then there's a multiple stress creep recovery test, or massacre test, as they call it. And also Hussein already told a little bit about those. Then we made in another university, in Queen's University, also PG, but in the sense of physical hardening. So we included for regular PG tests, we included extended PBR, we included modified PAV, and then we included DENT, which is double edge notched tension test. I'm going to speak about these a little bit later, briefly also. And then some needed modification to meet physical hardening requirements. Then we studied also chemical composition. We made chemistry with an elemental composition. We used Fourier transfer infrared spectroscopy. We used gas chromatographic mass spectroscopy. We used gel permeation chromatography. We used nuclear magnetic resonance spectroscopy. We are going to use differential scanning calorimetry. We are going to use thermogravimetric analysis, and we are going to do SARA tests. So these are the test methods we have been done for studying our bitumen chemistry and will study for bitumen chemistry. These test methods, we had to choose them according what possibilities do we have in Estonia. So if you read the literature about bitumen chemistry, you can see tons of different methods to use, different devices or different concepts to see bitumen chemistry, but not all of those are available in Estonia. So we were looking for those what are available in Estonia and what shows the good results in the literature. Okay, this is what we have done, and now some results. Here you can see results according to European Union. It's a quite messy table, a lot of small figures. Anybody who knows something of bitumen, they can read a lot of information out of it already. But just to summarize this table, all the bitumen meets EN regulations except this bitumen E, what comes to viscosity numbers. So bitumen E exceeds a little bit viscosity numbers. And also bitumen E is quite exceptional. As we can see, it has a very high softening point and very high breaking point according to Ring and Ball and according to Fraas. But it has a high penetration index and quite poor ductility numbers. When we look at the literature, already in 1972, paper by Norman MacLeod, he has stated that, well, I have modified it to meet the binder E. He has stated that binder E has a high penetration index and it fails in the ductility test at 5 degrees. This indicates that it is elastic due to the air blowing, and it is known to give early and excessive cracking distress in the surface. Also, ductility is likely a very good performance-based indicator if done at low temperatures, around 5 to 15 degrees. The pavements containing asphalt with low ductilities are likely to show poorer service than pavements containing asphalt of the same penetration but still high ductilities. So these are the very good literature points what we can point out when we look at this table, and afterwards you can see that these points are true. If you look at the high penetration index and the low ductility numbers, these are really connected to poorer performance for this bitumen. Okay, would you like to examine this table a little bit more, or can we continue? Yes. It's a standard for modified. Silver, am I right? Modified bitumen. This ductility test, is it according to standard? Yes. But it's for modified bitumen, yes. Yes. Well, as I said before, that we also included some tests what are related to modified binders to get more information about our binders. But penetration index and ductility, especially this ductility, it gives a lot of information also for neat binders, if we are talking about European test results. Then we made PG grading for preparing PG grade for a bitumen. I'm going to present you PG split grade. In the conventional PG, you have a 6-degree differences. So when you start at 50 degrees, then you jump to 56. But now we have split it into 2 degrees to have more information about what is happening in Estonia in reality, and to have more information about our bitumen, what are the split grades for them. So as you can see, when we take a split grade, then you could have plus 52, plus 54, and plus 56 degrees in Estonia. Well, plus 52 only here, that's the only spot, but basically 54 and 56. When we look at the lower temperature split grade, then you have a very huge variety of different, let's say, climate zones. And this split grade is very useful when we look at the low temperature properties, for example, -40. Bitumen, to achieve bitumen with so low properties as Hussein Bahia showed you on the chart, I don't have it in here. When you would like to have such a big differences between your high grade temperature and the low grade temperature, you would need to modify for sure this bitumen. And when you would like to achieve -40, you would need to modify it quite a lot. And that's a threat, as we are going to speak a little bit later about physical hardening. Why is it a threat? So rather to modify bitumen to meet -40, it is better to modify it -36, for example, or even 38. Otherwise, when we do our climate map or climate zones, as a PG says, as a 6 degrees, then you would have -40 everywhere in this region, and you would need to modify a bitumen in very high level. But that is not necessarily needed, because in the reality you could do, or you could settle in -36 or -38. Then we looked at the bitumen according to split grade. As you can see, these are neat unmodified binders. We have covered almost with all bitumen, we have covered the high temperature, but none of the bitumen could meet low temperature. So we have quite a lot to go from this low temperature to the point where we need it to be. For example, for binder A, you have a 64 degrees and -24 degrees, and you can see -24 only in here. So this bitumen, in the sense of low temperature, you can use it only in this region, not anywhere else. Okay. Yeah, I'm going to use this. This one, it would be easier for you to follow. So definitely you would need to modify this bitumen to meet the specifications as shown over there. Otherwise, you would have a lot of cracks, temperature cracks on your roads. Then also, as Hussein Bahia showed what they have done or how they have modified a bitumen. They have added some bio oils to binders, and then they have added some waste engine oils. I have marked a little bit different ways this VTEA, that's a vacuum tower asphalt extenders. So it's a, let's say it's a new commercial name for refined waste oils. And this ReOpe, that's a refined engine oil bottom. But let's make it simple and let's call all this refined engine oil bottom or vacuum tower asphalt extenders, let's call it as a waste engine oil. That's easier to follow. So they have used a lot of waste engine oil. Now, what this waste engine oil and what this bio oil does, so they make bitumen more viscous. So we can reach to, thanks to this, we can reach with our bitumen to more lower degrees. And you can see the results over here. So before you had here -24, now you have -28. But for example here, before it was -28, and now after modification it's -38. And as you can see, thanks to modification with polymer, we don't lose in high temperature properties also. If you go back here, you can see the modification. They have added quite a lot of oil and also a little bit modification with plastomer or SBS inside it, and the results are here. So now with this modification, our bitumen or those bitumens can meet our split grade requirements, what we have in Estonia or for the real temperatures what we meet in Estonia. Well, this is a BG. Now, how to transform those BG results to the results what we are familiar of? I can show you what has happened to penetration, what has happened to softening point, and what has happened to breaking point after modification with oils and polymers. As you can see that it's a tremendous change. For example, when you look at penetration, we don't use bitumen with such high penetration in asphalt concrete, never, because our experience shows that it doesn't work, isn't it? But according to BG, it does work. In the BG, we don't look penetration, or we don't look some properties in a very specific temperature. We look what is the needed temperature, what is the high needed temperature and what is the low needed temperature, and we tune our bitumen, or we choose our bitumen according to these. Okay, now bitumen has been modified. Is that it? Can we settle with that? There are very many articles that you can find what comes to doubt about oil and hybrid modification. Mikla asked, as you asked from Bahia about this also, what happens if you modify your bitumen with oil? And that's a very good question, because in the literature we can see that using waste and vegetable oils, they are a threat for premature hardening through gel formation, volatilization, exudation, that means varying from oils, and oxidation. Hesp and Sherwell in 2012, they have said that the typically large amounts of paraffin in waste oil residue makes the asphaltene fractions less soluble in the maltene phase, and this in turn predisposes the binder to accelerated physical and chemical hardening. Sheen et al. 2007, they talked about top, that is a byproduct of the pulp and paper industry. The top caused an increase in the aging index and reduction in the resistance of oxidative hardening. And similar effects is anticipated in vegetable oil modified asphalt, since both have multiple double bonds and are flocculants to asphaltenes. Wright et al. 2011. When you read that article, you can conclude that problems have occurred with binders containing both SBS and waste engine oil. As waste engine oil, it contains polyisobutylene, which participates the SPS, which can lead to serious problems. So what does all of this mean? What is this premature hardening, or what is this physical or chemical hardening we are warned about? Hess et al. 2007 has stated that reversible hardening can broadly be defined as a gradual stiffening of a material during isothermal storage at low temperatures brought about by changing in the bitumen structure. So that is a wax crystallization, asphaltene aggregation, and volume relaxation. The effects of physical and chemical hardening are very similar. Both processes originate from the imbalance between the solubility properties of the asphaltenes and the maltenes. And that means when maltenes lack their aromaticity to solvate or peptize asphaltenes, a gel-type structure is formed with a high viscosity at low temperatures, leading to premature and excessive thermal cracking. So, to illustrate, the results are here. When we have modified our bitumen to withstand those temperature cracks, but we have modified our bitumen in a way that it suffers from physical hardening, still this is happening because of the grade loss. I'm going to show some results a little bit later. Of course, there's a different view of using oil modification. Some people say that it is okay, there's no worries about, because those statements over here, reversible hardening, it comes from Queen's University, from Professor Hesp, and they said that in Professor Hesp's study he have used waste engine oil in the range of 15 to 30%, which is a very high percentage or very high amount of oil added in bitumen. In the reality, commonly what they put inside the asphalt is less than 8%. So they doubt that is this reversible hardening so bad as they say. Also, in another study, they stated that our study indicated that there isn't any rapid hardening in the asphalt binder or mix with the waste engine oil. So they claim that it's not a problem reality in this study, because they don't use as much waste engine oil as 15 or 30%. They use more or less. And also they say that the data clearly shows that there's no cancer-causing materials in waste engine oil. So it's safe also for humans and also for roads or pavements. You can do it, you can modify it because it's a cheap way to do it. Well, that was a different view of using oil modification. But still, considering that reversible aging at low temperatures is likely and serious cause of premature and excessive cracking at low temperatures, a 6-degree loss in low temperature due to a 6-degree loss in low temperature grade due to this process will reduce the confidence that a given road will not be exposed to damaging temperature from the intended 98% to less than 50%. When we go back to this map here, as you can see, well, it is in Estonia, but here you can see that confidence that this temperature will not go up to minus 36 degrees or this temperature go up to minus 34%. The confidence is the confidence is 98%, though basically it never happens. So when we put a bitumen inside, which has the low temperature grade for minus 36 degrees, there will be no cracks inside it. But when we use a modification with oils, then we reduce this confidence for 98% to less than 50%. So there's a big grade loss, and in the results we can see this kind of damage on roads. Well, these are not very bad damage. There's a lot of worse cases. Okay, how to overcome this? We have studied reversible hardening with 3 different methods. First of all, it's extended PBR. It's a LS308 in Canada, as they call it. And with this, they condition bitumen at 10 and 20 degrees above the minimum design payment temperature for periods for 1 hour, 24 hours, and 72 hours to simulate the effect of extended exposure to different cold temperatures. And investigation of 20 paving contracts in eastern and northeastern Ontario, Canada, found that by measuring the creep properties after this 1, 24 and 72 hours of conditioning in extended PBR, the accuracy of the performance grading increased from 50 to 55%, that is for normal PBR, from 55% to a range of 80 to 85, well, 90 to 95%, that is for extended PBR, depending on the exact specification criteria that were chosen. So we have from 55% to 95% accuracy, whether you use a regular PBR where you don't consider reversible hardening, or whether to use extended PBR where you consider reversible hardening. So you can be much more confident that this binder will perform in very good way on the road, and you cannot see those kinds of cracks on the road. Okay, what are the results? These are neat binders, unmodified, and as you can see, let's focus only on this over here. Here you can see true grade PG grading, also some extra testings, what happens to high temperature or how much bitumen hardens during aging. But let's focus on this chart here. So it shows that according to extended PBR, after 72 hours of conditioning, you are going to have up to 7.1 degrees of grade loss. That means originally you got that this bitumen will withstand minus 31 degrees. So you can use this bitumen minus 31 degrees. You can use that, well, not so big area, but just to illustrate, you can use that bitumen in this area over here, minus 30 degrees. And when we condition that bitumen for 72 hours, it loses, it's a 7.1 degrees, and the left is 24.2 minus degrees. And when you look at this map, it shifted from minus 30 degrees to minus 22 degrees. So for sure, when you use this bitumen here, and you are confident that it will withstand for minus 30 degrees, but in the reality, when there's a physical hardening going on, then the minus 30 shifts to minus 24 degrees, and for the results, you can see a lot of cracks on your roads. So that is the physical hardening. As you can see, there are two very good binders that doesn't have any, or that doesn't suffer any physical hardening. So you can be, with these binders A and F, you can be confident that nothing happens during the time. There's no isothermal processes going on what could damage this asphalt. Also, UW Mark made extended PBR for modified binders, and you can see that up to 24 hours conditioning, everything is okay, but when you condition the samples to 72 hours, things are getting worse. Yes, I have mixed two results together for bitumen A. There's a PBR at minus 18 degrees, that means on the field, that means 28 degrees, and for other binders on the field, that's 34 degrees. Those bars, they cannot reach above this line, or they have to go above this line. So when they fulfill those requirements, then we can say that it meets the required temperature. When we look at this conditioning, we can see that M value is the controlling factor, and nearly all binders will fail after extended PBR test that they suffer a lot of physical hardening. From this chart, we can say that higher polymer contact showed to be more effective than oil modification. For example, when we compare binders C and G, these are from the same crude and they have very similar physical hardening figures for unmodified state. When you look at this C, it has a physical hardening rate or grade loss 5 degrees, and when you look at the G, you have a 5.1 degrees grade loss. And when we go back to modification, we can, for C and G, there's the same amount of oil, but for C, there's a 3% of SPS, and for G, there's a 5% of SPS. So for G, there's a more polymer inside it. And when we look at the results, then for C, it does not fulfill physical hardening requirements, but for G, it fulfills physical hardening requirements. Well, of course, there's a slight difference between that C is a penetration 7100 and then G is a penetration 160 to 220. But this conclusion also, we can validate this conclusion also with a support of literature. Wright et al. 2011 wrote that lack of significant thermal cracking distress was likely due to high polymer contact, providing a significant strain tolerance. Sanagata et al. At 96 studied 16 different modified binders and concluded that no simple effect of the polymer modified can be found and that different polymers have widely different effects on the aging rates. EVA copolymers were found to make the hardening worse, while EMA and SPS copolymers were found to lessen it. Also, polymers such as SPS can increase the elasticity of the neat binder, which results in higher endurance and reduce the susceptibility to thermal and fatigue cracking. So we can see that in the literature, we can see that SPS helps a little bit to withstand reversible hardening, and we can see from our results then that is true. Well, we have only 2 comparable points, but in here we can see the results. Also, to see our results, we can see that adding oil made physical hardening worse. When we compare bitumen A and F, they are from the same crude and they have a very similar physical hardening figures for unmodified state. As you can see here, neat binders, they don't suffer at all from physical hardening, or they don't have any grade loss. But when we add oil inside it, as you can see, for 72 hours conditioning, physical hardening goes up in a very high level, and also obviously, so this shouldn't exceed this red line, and this should exceed this red line. It doesn't show, it shows that there will be some very bad physical hardening happening inside it. So oil modification made physical hardening worse, and also we can conclude from this that literature is on a right way. Johnson and Hesp concluded that waste engine oil should only be used with great caution for the modification for low asphaltene binders. Okay, I'm gonna skip this because my time is running out. We have done reversible hardening and fatigue study also with double-edge notch tension test, LS299 or DENT. It also shows very good correlation between how binders are acting on a field and how binders are acting on these tests. DENT is considered as one of the tests for fatigue properties, and also Professor Bahia told a little bit about LAS, or how do you call it, linear amplitude speed test, but is also should go for fatigue properties. But here we can see very big differences in the sense of binder E. E does well in LNAs, but will likely perform very poorly in service due to lack of durability. So linear amplitude sweep that doesn't consider durability of bitumen, but dent does. And the third one is modified BAV, so they have modified long aging procedure a little bit to also have more information about bitumen, and again we can see some not so good results from bitumen, which shows also not so good results for age hardening or reversible hardening. Then we conducted chemical study. Bitumen is very complex material, and describing it in the sense of chemical composition, that is not an easy task. But we tried to do that, and as I showed you before what kind of test we done, now the results. We made an elemental composition. Over there we can see bitumen fingerprint, and we can assume a little bit about how fast or how slow is the oxidation in bitumen. Also, additional X-ray studies showed that no zinc or molybdenum content was in our bitumen, so no waste engine oils at the moment inside it. So these physical hardening figures, as you can see here, these are not because of the waste oil. These has to be from some another source. Then we found out in the literature that vanadium is known to promote the aging of bitumen through oxidation of the carbon matrix. We found some little bit correlation about this one, not very strong correlation, but still we saw that vanadium, at least in this case, could promote the aging. Then we made an infrared spectroscopy measurement. There comes a fingerprint, what is happening during aging, and indication is bitumen straight run or air blown. Air blowing technology is not so good because, well, I have wrote it down here from Hess particle 2007, that when asphalt with insufficient aromatic maltine fractions, asphaltenes are not well dispersed and can again, difficult word. Yes, interconnected structures which form a continuous network throughout the asphalt in extreme cases. And these kinds of asphalt are called gel-type asphalt. They have low temperature susceptibility, low ductility, significant trioscopic properties and elasticities, and high rates of age hardening. So these are the reasons why we wouldn't like to see air-blown bitumen inside our payments. And infrared spectroscopy could relieve us which kind of binders are air-blown or which kind of are not. Then we made gel permanation chromatography study. It shows again how fast or how severe is the aging, how different sizes of molecules, how they are changing the places, and then also GPC enables to determine average molecular weight. So we could find quite good correlations between average molecular weight and low and high temperature grades. Then we made gas chromatographic mass spectroscopy study. Over there we show short and long chain hydrocarbon content, and as you can see that N-paraffins that are long chain hydrocarbons, they are inside a wax and they tend to crystallize, and again from the literature they appear to be no binders with a high wax content and low grade loss. This provides indirect evidence that the amount of wax in the binder at room temperature is an indicator of the tendency of the material to reversible age at low temperatures. When we look at this graph, here you can see content of long chain hydrocarbons or these N-alkanes, N-paraffins. You can see that inside the binders D and D, there's a very huge amount compared to others. And when we go back to the slide, which shows us reversible hardening, you can see that D and D, they have a highest grade loss inside it. So we conclude from that they are not oil modified, so this oil modification doesn't make grade loss so big, so it could be wax that wax causes this big grade loss inside it, and we can see the results over here. We don't know the wax content yet. We would like to do DSC and TGA studies. We know that some countries have set a limit to wax content to overcome this reversible hardening, or to overcome some other factors too. And we would like to see, can we see the relationship between wax percentage and our bitumen behavior. We haven't done yet Sara fractions. It is expected that a good balance exists between both the polar and non-polar molecules in order for the asphalt to show good performance in service. So maybe we can draw some conclusions out of there also. We don't have the results yet what comes to modification to meet BTA and physical hardening requirements. So how can we modify our bitumen without using waste engine oils to meet those temperature grades we are having in Estonia? And also we are having DSR study at the moment, what is happening with our road, with our bitumen on the road, how fast is the aging rate, and then we can compare PAV results to the real situation what we have on the paved roads in here. As I said, we cannot draw out final conclusions at this moment, but some preliminary conclusions. We can say that according to BT and massacre tests, our bitumen high temperature grade or high temperature is covered enough with our studied bitumen, and bitumen is not the reason why we see ruts on our road if we include studied tires. And we can clearly see that our bitumen problem is low temperature and physical hardening, also fatigue properties. Suggestion for the future, as also Hussein Bahia told that the system is complex. At the moment we only have covered bitumen, but also mastics or filler and asphalt mixtures, they are very big influence how our pavement works. So it would be nice to have those next to make the circle closed. Also moisture damage is a question, but this has to go with the mastics and asphalt mixture study. And definitely we would need some test sections to validate the study results what we have from this point. So thanks for your attention. Thanks again for road administration for a financial study, and that's it, if you have any questions.
Thank you very much. It was a very, very thorough work. I'm really impressed. I'm Helena Odelius from Nynäs. I'm technical manager of Bitumen Nordic in Nynäs. And I think it will be very interesting results coming out of this. I haven't seen in a long time such a thorough work. I would like to comment on the question about what to do if we don't want to use engine oil. I think one major difference between the Nordic countries and the US is that there is availability of soft-grade bitumen in Nordic. So with soft-grade bitumen and PMB modification, you would be able to reach -40, I'm sure, and we could look into that more thoroughly, I think, because then you will have your control over the quality of your base bitumen. You don't need to add things which are not specified in bitumen standards, which can help you reach the grades that you need.
That's a great comment, thanks. We have been discussing exactly that point with each other, and as you can see from this chart, that modification made penetration very much bigger numbers, that is a possibility to go that way, yes.
Thanks. Edvinas Peletskas, how would you see Sasobit as a special works in combination with SBS modified bitumen? Are you planning to study it? Because in practice it's quite common to have such a combination.
Yes, I don't have an answer right now for that question.
In the future.
Yes,
Thanks.
but of course suggestions are very welcome, and there are some possibilities to continue with the study, for example, by our own, and then we can see another possibilities, another ways to modify bitumen, or what different components, how they act together. I think we have some experience from the field already about this question, but I'm not quite sure about the results yet at the moment.
Some more questions?
Audrius Vaitkus, Vilnius Gediminas Technical University. I would like to raise two questions. One question I would like to get answer now, if you could, and the other one for panel discussion. And for panel discussion, I would like to ask, how do you think to solve legislation problems, because it's EU legislation, and PG grading is it could be a lot of problems with that. And how do you think to do that? Because this question is important not only for Estonia, but also for all Baltic region countries. And the question for the presentation, I would like to ask, how did you make the regioning of Estonia to 4 regions, and do you use the frost penetration data from weather stations? And if yes, for how long year period you took data?
Thanks for the comment. We made the map according to PG regulations, or what comes together with PG, so we used weather station data. I cannot remember, 20 years, 20-year time we used.
From the weather stations? Or
Yes.
From,
well, was it the
hydrological zone?
It wasn't the road weather station, because we don't have such a long data for those, but we used meteorological
But
data.
the main problem what we discover in Lithuania, that the data for frost penetration from these weather stations of meteorological departments is completely different which are in the roads payment structure.
Yeah, that's a frost problem, because when you have a land covered with snow, then the cold heat cannot penetrate. But on the road, you have a bare road without snow, so you don't have isolation. But in this case, you wouldn't need to consider frost dip, because frost comes together with frost heave. In this case, you have only top part of pavement. So it's a temperature on the ground, not beneath the ground.
I have also one question to you, Sven. That was you
should know everything already.
But it was about the penetration, and you mentioned here that we should use softer binders in our asphalt mixes.
Well,
but it's like a recommendation, of course. But according to PG grade standards, but how we should move into this change, because it means, of course, that we have to start to change the mix design, and what steps we should do in this.
I'm a scientist, and well, I would like to consider myself as a scientist, and I'm in somehow quite crazy guy that I would like to, without no thinking, just to buy everything inside and then forget EU standards and to do like we find in here. But yeah, regulations, legislation, that's a very good point, and we have to see how to overcome these points.
Because we just can't change the binder that's like this to a softer one and start to do the same mix design. So we have to actually.
As we raised up the question, what is good binder, what are the properties, how to measure the limits, how to measure this binder. So I think we can figure out the answers, but how it works in the reality for the sense of legislation and the European Union. Well, I'd like to say that I'm a scientist and I would like to do a research work, but I don't care about legislations.
Okay, thank you, Sven, and for the questions and the answers as well. So I have a small present for
Thank
you.
Thank you.
Thank you.